When I say rigor, you say mortis. Rigor, mortis, rigor, mortis. All right, you get it. So we have a fish. It's gutted. It's dead. We've taken everything out of it, and this thing's still flopping. We have a chicken. Raw chicken bone. It's dead. This thing flops off the plate. How is this possible? Well, let's get right into muscle contractions. The first step in a muscle contraction is known as excitation at the NMJ. So basically, when your brain is ready to contract, it's going to send a nerve impulse down the axon terminal, which is known as the action potential. Right here is a perfect diagram of the neuromuscular junction. We have a nerve over here, we have a muscle down here, and then all of this in the middle is the junction. So all together we have the neuromuscular junction. This contains everything we need to create excitation and contraction, muscle contraction. We have our calcium gated channels here. We have our sodium channels here, and we have our acetylcholine receptors here. These are our vesicles, which are going to move the acetylcholine down to the sarcolemma, and where the calcium ions will be released. Once the ACH binds to the receptors of the sarcolemma, the acetylcholine opens the voltage-gated calcium channels, which allows the calcium to rush in and enter the neuron. This generates our action potential. Once the sodium ions rush in, the charge becomes a little less negative, and this begins depolarization. Depolarization gives us the potential for a new action potential, and this is gonna basically come in and steal the show, because this is what's gonna lead to the end of our muscle contraction. The diffusion of the acetylcholine will go across the membrane, and anything that is left over will be pumped out or eaten up by acetylcholine esterase. Once all the acetylcholine has diffused, this will help so that our muscle can no longer contract. So basically, none of this can happen without calcium. So the calcium needs to enter these channels, but that can't freaking happen without an action potential. Isn't it just amazing to think that such a small muscle movement and, different contractions have to go through so many processes? I mean, who finds this interesting? Raise your hand. Go Patriots! And on to better news. Next to Danielle to help us understand ECC. All right, so again, calcium channels open, calcium comes in. These vesicles right here that contain our acetylcholine release down here into the synaptic cleft, down to the receptors. Once the acetylcholine reaches these receptors, sodium ions rush in, potassium rushes out, and this creates an action potential at the end plate. Once all of the acetylcholine diffuses, it goes back to repolarization. So again, we need calcium. We need these channels to open so that calcium can go in, and we can't freaking do this without an action potential. So when you stop to think about it, isn't it pretty amazing that, all these little muscle contractions, something that you don't even think twice about doing, pick up a pencil, blink your eye, whatever it may be, all of this stuff, all of these moments that are creating action potentials, from the nerve impulses from our brain, they all have to go through this process right here.
I am so excited to talk about excitation contraction coupling with Toby. Look at Mr. Man. He's excited too. Do you think it was Felicia's chant? Rigor mortis, rigor mortis. I don't know, that got me pretty excited. Honestly, the did you guys hear that? Something just fell. Excitation contraction coupling, otherwise known as ECC, couldn't be here without NMJ. So thank you, Felicia, for telling us all about that. I'm gonna move my face over here a little bit. Toby had to join us. I apologize, everyone. He's something else, right? So as I was saying, ECC really couldn't be here without NMJ. And that's because muscle fiber, once the muscle fiber depolarizes, it travels or it sends an electronic. I keep messing up. I've recorded this like 5 times, so I'm just going to keep going with it. Especially since Toby's in here now. Maybe he'll get me extra points. All right. Let's start that over. So once the muscle fiber depolarizes, sends electric signals through T-tubules. T-tubules are tiny tunnels found in muscle fibers. So inside the T-tubules, as I previously mentioned, are tiny tunnels running through muscle fiber. I have another prop. It opens calcium channels in the sarcoplasmic reticulum, and it floods calcium in. I hope this isn't mirrored. I hope you can see what I'm writing. So the calcium floods in and it binds to troponin and it shifts the tropomyosin out of the way and exposes active binding sites. So it exposes active binding sites so the muscle can contract. Calcium doesn't necessarily it's not in control of movement, but it's more like the key to unlocking the door. I'm a mess. To movement. So next, Julia is going to explain what's going to happen. Are we going to find out why we have a raw kickin' chicken and a dead flopping fish trending on social media? I don't know if it's Felicia's rigor mortis cheerleader chant or the excitation contraction coupling, but I'm really excited to find out.
Thanks, reporter Danielle. I'm reporter Julie, and here we are continuing our breaking story of what is going on with the dead chicken and the dead fish, and why are they still moving? Well, here I am to solve a piece of this puzzle. And here we can see the cross-bridge cycle. Now, as my colleagues before have described the steps previous to this, we will now discuss the cross-bridge cycle. So, our first step is the cross-bridge cycle formation. Now, see what happens is calcium here, this tricky fella, he binds to the troponin. And what happens is the troponin then changes shape. And that lovely, lovely little tropomyosin ends up switching a little, opening these little active binding sites to where the myosin actively binds to. What happens is now an amazing process. The myosin heads then with ADP and phosphate. They then anchor themselves and attach themselves onto the myosin binding sites. Shocking, I know. And we can see what happens next. If you bear with me, my colleagues. Our second step, dun dun dun, the power stroke. Now you can see the myosin heads have binded to the active binding sites. on the actin, the ADP, and the phosphate. Then, like a rope grabbing, boom, pull the power stroke, allowing the myosin head to pull the actin. Now this is an active step in our contraction. What happens is, while this is going on, is that the myosin pulls the actin towards the M line. So it gets smaller. Now, it needs to be noted that the A band doesn't actually change its size. It does stay the same size. But however, this myosin head is pulling the actin towards the M line. So the M line is going to disappear in the H band. Now, let me scroll over here. Our third step is a cross-bridge detachment. So even though ATP does play a role in, our muscle contraction, it doesn't actually cause the power stroke. That is the active energy, which is ADP and the phosphate. ATP is inactive, or like passive energy, right? So, not that it's active, but what happens is, in order to unhook from the myosin binding site and restart the process all over again, we need this little fella, ATP. What does he do, you ask? Well, I'll tell you. What he does is he gives the myosin head the little oomph so that the ADP and phosphate detach. And the ATP, boom, it allows the myosin head to unhook from the actin binding, the active actin binding sites. And then you can see, my friends, our next step is the cocking back and resetting of the myosin head. The fourth and final step. Now, once the ATP has allowed the myosin head to unhook itself from, or unbind itself from, the active binding sites on actin, what will happen is that ATP allows it to reset itself. And, the ADP again and the phosphate come in and play their role to reset the myosin head so that it can pull that rope again, like in action. Boom, boom. And it has to follow these 4 steps in order for the cross bridges to form, but also the heads to actively bind, do the action of pulling with the ADP, the power stroke, then use ATP to detach and reset itself with ADP. So it's quite a process. However, I know that it must have something to do with this dead fish and chicken. And of course, we also have to talk about the sliding filament theory. Reporter Julie back. Thank you for bearing with me while I fixed my screen. But I do have a second portion to this, and I think this tricky guy might have something to do with our dead fish and moving chickens. Now, we're going to discuss something tricky called the sliding filament theory. What is that, you might ask? I'll tell you. Well, the sliding filament theory states that the thin filaments, they slide past the thick filaments right here. So you see, we have our actin, our thin filaments, and our myosin, our thick filaments. You see, the sarcomere goes from Z disc to Z disc, and the A band consists of this portion right here. Now, it should be noted that our I band right here, the I bands will shorten during contraction, and the H zone rather, they do shorten and disappear, and the thin right here will slide. The thin filaments will slide toward the M line. So that's what actively is happening in the sarcomere during contraction. So the A bands, they do move together, but they don't actually shorten. So if you can see. So basically what happens is, like the rope pulling, the muscle wants to, when it contracts, it wants to shorten, right? So what's going to happen is the myosin in the sliding, according to sliding filament theory, the thin actin filaments will be pulled or slide past the thick filaments, the myosin. And what happens is they will get closer and closer to this M line. And that's what's going to obviously shorten the sarcomere, the muscle, the unit of muscle. And that equals it getting smaller. Although the A band doesn't, it doesn't actually, it doesn't shorten, but, the contraction happens because the actin is being slid over the thick filaments. And so it comes together. And like the pulling and the releasing of the rope, that's what causes the movement and the contraction of the muscle. But that takes place in all the sarcomeres happening simultaneously throughout the muscle fiber. And so that equals the one muscle doing a full movement. So, I think this guy right here could possibly have something to do with our tricky fish and our tricky chicken. Fishing. Well, I think, it might also have something to do with it because as long as ATP and calcium is available, we know that the muscle will continue to contract. I don't know though, but what happens, if there's no ATP? And what happens if calcium is still available? Ooh, these are all tricky questions. I think in order to round out this, we got to pass it over to my colleague, Jerry. Take it over, Jerry.
Good evening, good morning, good afternoon, depending on the time that you're seeing this live broadcasting. So previously, you guys already heard from my colleagues, Felicia, Danielle, and Julie. Just previously heard from her. And we're pretty much discussing why does it still move, right? So let's go ahead and put our thinking caps on and let's close out this case. So why does it still move? So you just recently learned about the neuromuscular junction. You learned about the excitation, contraction, coupling. You learned about the cross bridge. I'm here to talk about why does this actually move, right? So we previously just got these two videos from our professor, Dr. Wong, who pretty much showed us two objects, which I'll show you guys a little clip in a little bit, but pretty much a headless fish and a headless chicken. Both have no guts. Both are pretty much on the verge of death, right? So quickly to touch on the process of death. What happens, right? So you have your cessation of the vital functions. The heart stops, right? You stop breathing. You're dead. Boom. Done. Your brain cells die within minutes. Then you enter into body cooling, and then you enter into rigor mortis, which we'll talk a little bit about that. And then, of course, you decompose and become food for the animals and the worms, and you get put 6 feet underground, right? Yeah. So how does it still move, right? So in these two videos, I just captured little snippets where you can see the fish with no guts, no head. The chicken, it looks like it's ready to be stewed, cooked, grilled. But why does it still move? But before we get into the reasons why it would still move, let's talk briefly about parts of death. That sounds very interesting because when we think about death, we think about a cold, stiff body. But in order for it to become that moment, we got to understand who is in charge here, right? So is the muscle in charge or is the nerve system in charge, right? And in layman's term, the nerve system is in charge. It controls the body. Your muscles do all the heavy lifting. So you walk, you run, you lift, you bend over, you exercise, you go through torture in your body. So muscle system equals action and movement. Nervous system equals your control center. In order before you enter into decomposition or during the process of decomposition, there's a moment in your body where everything stiffs up, right? You just lock in, you can't move. Comes to a point where as morticians are doing what they do best, in order for them to get like a piece of jewelry off, they obviously can't just like pop it open. You know what I mean? There's certain movements where they have to like bend down your muscles to get some sort of reaction to then release it to break the rigor mortis or the rigor from your muscle stiffness. So that pretty much is muscle stiffness. Cool. There's probably some Latin thing about it. I don't know. I ain't gonna get that in detail for y'all. But during this investigation, we learned that 2 to 6 hours after your death is when rigor mortis would kick in. Your peak stiffness is about 12 hours after death. And then 36 to 48 hours later, or actually 48 to 36 hours later, my math was completely wrong. You can tell it's very late at night. Your muscles will start to relax and start to break down, and that's for the whole science piece of it. But things that would affect your timing of death or kick in decomposition a lot faster, obviously your environment. Right now we live in New England. It is cold as hell. So that means I'm stiff because it's cold, but I'm still alive. That sounds so wrong. Warmer environments, obviously. So if you're in the south, your decomposition process will start sooner. Obviously, your body conditions, muscle mass, your physical activities, what you do before death, what you do after death. After death, what you've done. Obviously, certain things could also affect like sickness and stuff like that. So there goes that shebang. Um, but why would the dead fish and the chicken move? Obviously, talking about your timing of death, right? Warmer environments, colder will kick it around. Obviously, one of these would look like probably in the South, right? Just a Southern person picking up on other Southern things. But also that's how they're able to identify the time of death, right? So freshness there, killing it. That sounds so bad. The freshness of your death, like if we're going to like eat you now. But we see here that both the fish and the chicken are attached to bone. Well, more the fish before I get into the chicken, but the um, fish still has its spinal cord. So remember previously I said that the nervous system is in charge of your body, right? So it's kicking and hollering, hooting, because there's still some residual nerve energy there. So there's still nerves and muscle fibers that are firing, motions to move, right? The spinal cord is still storing all of that residual energy, which can cause some muscle spasm. So as the lady is trying to grasp the tail to skin the chicken, obviously it's going to like high alert gear, like, hey, something's attacking me. Let me try to swim away. But that's just because of the residual nerve energy that still is in play here. So it's still stimulating to move because it still has its muscle, its spinal cord intact. So at the end of the day, it can still move. Is it common? Possibly. I mean, I kill fishes to eat, not to record a video. Please excuse my dogs in the background. They didn't want to be part of the video. But we also come to learn that the ATP is still involved, which you probably heard my colleagues and anchors, Julie, speak previously. But that's how we've come to discover that there's still a process in play, right? From the action potential motion. It is very late at night, so I'm not speaking English. I will be very honest. But pretty much they're still charged through before the ADP kicks in that will break the cycle and start to decompose. So I hope you learned. Thank you so much for watching our news podcast. I hope you learn that I don't speak English, but I do understand that. Have a good evening.